Now, let's discuss what defines the resistance of materials and what creates resistors. You might have heard of conductivity value of a material. So conductivity sigma tells us how good a material is in conducting electricity. Well, resistivity with units of ohm meters is just the reciprocal of conductivity, and it tells us how good the material is in resisting current. So if you're comparing the resistivity value of insulators versus conductors, if you remember from lecture 1, we said that the difference between energy band diagrams of insulators and conductors defines how much current is created when we apply a voltage around them. So for an insulator such as hard rubber, the resistivity value is going to be somewhere around 10 to the 13 ohm meters. Whereas for conductors such as copper and silver, the resistivity value is going to be 1.5 times 10 to the negative 8 ohm meters. And if you see, there's a huge difference between these two different types of materials because of the difference between their energy band diagrams. So when a material is manufactured, let's say it comes in the shape of a rod or a cube, a cube is not a cube. If the density of these two materials is the same, then the resistivity value of these two objects are also going to be the same. Now, the size of these two objects and the length of them are going to matter when we're calculating resistance of it. Now, resistance R, unlike resistivity, does discriminate size, and it's just in ohms. So let's say we're trying to calculate the resistance of this rod over here. We're just going to place an ohm meter around it. This ohm meter is going to apply some voltage V around this material, and then it's going to measure current. So then using Ohm's law, it's going to say, hey, V applied divided by I measured is equal to the resistance. Well, what if we want to calculate the resistance of this rod without this ohm meter? In that case, resistance R is going to be the resistivity of the material of this rod times length, and length is just this distance that electrons have to travel before reaching the destination of the object divided by area. And area is this cross-sectional area that all these electrons have to travel through. Now, is it intuitive that when my length increases, my resistivity also increases? Think about it. If my length increases, then these electrons here have to travel a longer distance before reaching the end of the object. They have to work harder, they have to go through more resistivity, and because of that, the path becomes more resistive for them. So R increases with length. Whereas if we increase this cross-sectional area, we're feeding more electrons through the same window. And if we fit more electrons, we're allowing more charge to pass through it. And if you remember, current is the rate of charge. So if I increase my area, I'm allowing more current. So my resistance goes down. And let's do a unit check over here. My ohm meter, my resistivity is in ohm meters. my length is in meters, and my area is in meters squared. So all these meters are going to cancel out, and you're just going to have ohms for resistance. If you look at the resistivity rating of a material, you'll also see an associated value of temperature. And this means that my resistivity X is only valid when my operating temperature is Y. So this means that my resistivity is temperature dependent, but different types of materials behave differently to change in temperature. So I have superconductors, which are known for their unique temperature, below which their conductivity drops to almost zero. And this means that if I have a superconductor wire operating below Tc, it's going to create little or no resistance to the path of the electrons. And that's good because it minimizes our resistive losses. It minimizes the I squared R. And then we have semiconductors. If you remember from lecture 1, we said that the energy band diagram of semiconductors looks something like this. We have the valence band, conduction band, and there's a small energy difference in between these two. So with semiconductors, if I increase my temperature, what I'm doing is I'm giving enough excitation to this electrons in the valence band to jump to the conduction band. So I'm creating more delocalized electrons. Therefore, I'm creating more current. And as a result, my circuit becomes less resistive. Compared to metals, we said that the valence band and the conduction band have an overlap section. That means if I provide more energy to electrons, they're not going to go to where they already are. They can already exist in the conduction band in the overlap section. So with metals, what happens is that with increased temperature, I get more phonon electron interaction. And what this is that with increased temperature, my atoms start vibrating more. And therefore, my electron clouds start vibrating more. And they start colliding with my current electrons, with my delocalized electrons. So because of that, my material becomes more resistive to current. So my current goes down, and therefore we can say it's more resistive. And you can see that the relationship between resistivity and temperature of conductors is linear. So the equation that we're given for resistivity of metals is the following, where we have two rated values. We have one constant, which is our temperature coefficient of resistivity. And then we have two variables. So let's say I've been given the information that my material has resistivity of 1.5 times 10 to the negative 8 ohm meters, which is a conductor, at temperature of 20 degrees Celsius. And I've been given that alpha is, for now, let's say 0.01. Now, I'm trying to find what my new resistivity is going to be at a temperature of, let's say, 50 degrees Celsius. So over here I have that at 20 degrees Celsius it's somewhere around 1.5 times 10 to the negative 8 ohm meters, and I'm trying to find this value over here. So let's use this equation now. So my new rho is going to be 1.5 times 10 to the negative 8 times 1 plus 0.01 times 50 minus 20 degrees. So I'm going to get 30 degrees difference, and my answer is going to be 1.5 times 10 to the negative 8 times 1 plus 1% of 30, which is 0.3, is going to be 1.3. So my new resistivity now is 1.3 times 1.5 times 10 to the negative 8. Resistance is not always an uncontrolled variable in circuits. We can use resistance in circuits to control current, and components that are made to do so are called resistors. So here I have an example of a resistor, and on the resistor you can see some color coding. And if you look up the color coding table, you can calculate what the resistance value is. So the outside coating of this resistor is an insulator that's protecting whatever that's inside. So if I zoom inside, I'll see two things. I see a ceramic carrier which is a non-conductive material, and I see a carbon film wrapped around the ceramic carrier, which is a conductive material. So it has some resistivity rho to it. So if I connect this resistor to a voltage source, what's going to happen is that I'm going to get some current from the positive terminal of this voltage source to this resistor, and my current is going to go spirally through all this carbon film until it exits out from the other side and goes back to the voltage source. Now if I take this carbon film and I stretch it, I'm gonna see something like this. So this is our carbon film. It has a length L, it has some thickness to it and some width. So the manufacturer, when they want to create a resistor, they can't just guess what resistor they're gonna make. They use the equation we discussed before, which is R is equal to rho times L over delta T to delta W, to calculate what the resistance they want to get. So with adjusting any of these variables over here, L, delta T, and delta W, they can get the resistance they desire. Now you might ask, why is this resistance, why is this carbon film spirally wrapped around the ceramic carrier? And the reason for that is that this L is much bigger than the size of the resistor. and we want to use the resistor in our circuits, so we need a compact component. Now let's draw the schematic of this circuit over here. So I see a 1.5 volt DC battery that is connected to a resistor. And this is how we indicate resistors in schematics, the spiral shape of it. And so the resistance of this resistor, we can calculate it using the color coding table. So we have two reds, one orange, and one gold. So looking at the table, I know that this is a 5% tolerance value, and then the value before that is a multiplier. So multiply by 10. Orange is 3, so 10 to the 3. And then red is just the value 2. So then my resistor is a 22,000 kilo ohm, plus or minus 5%, we don't care right now. And sorry, not kilo ohm, just ohms. So it's a 22 kilo ohm resistor. And one more thing that I'm noticing here is that I'm using a conductor, let's say copper here, to connect this battery to the resistor, and this copper has some resistivity value to it. And let's say it's 1.5 times 10 to the negative 8 ohm meters. So then I need to model the resistance that this copper is going to provide to my circuits with another resistance, with another resistor in my circuit. So the value of R1 is going to be 1.5 times 10 to the negative 8 ohm meters times the length of it, which we're given is 10 centimeters, so it's 10 times 10 to the negative 2 meters. I'm converting everything to meters, and then it's divided by pi r squared. So it's my radius is 2 millimeters divided by 2, so it's 1 millimeter. So 1 times 10 to the negative 3 meters squared. Now I'll plug all of this in my calculator, and I'll get my resistance is 4.77 times 10 to the negative 4 ohms. So I'm going to replace this with 4.77 times 10 to the negative 4 ohms. Now look at the difference between the resistance that this conductor provided to the circuit versus a resistor we use. The value of it is 1,000,000 times less. So because of that, in the future examples, we're going to ignore this small resistance that our circuits, that our conductors provide to the circuit. And we're going to assume that they're zero, and these guys are perfect conductors. So R is equal to 0.